Okay. Three. Just one. So yeah, we are going to answer almost every question in this question. I can say every question. Yeah, all the questions in this question paper are going to be answered. And I would also explain where I have to explain. So yeah, containers of gas that are connected by a thermally insulated tube. Container A is surrounded by an adiabatic boundary. Would you describe the system? Justify your answer. Type of questions need you to validate when you are sure of. You have so this from here. The adiabatic that I'm talking about is this one. This one. Adiabatic boundary. Container A is surrounded by an adiabatic boundary. Will you describe the system boundary as adiabatic or diathermal? Now you are going to talk of the whole system now. Is it adiabatic or diathermal? Because in this case, here you don't have heat exchange. But what about here? There's no boundary here. So it means heat can exchange with the surrounding. For B, heat can be exchanged with the surrounding. Meaning, when heat is exchanged with the surrounding, what does that mean? It means it's going to be diathermal. Instead of adiabatic, it's going to be diathermal. So, but now, what you also have to think of, this question or this type of question, you can answer it in two ways. You can choose the system boundary as adiabatic, and then you justify your answer, which is what I'm going to do here. Also, you can choose the system boundary thermal, and then you justify your answer. Based on your justification, you'll get your marks. So this is how we are going to. Okay, before I can go and write it down, when you state that it's adiabatic, you are going to justify that we are assuming that if this separation between A and B is very, very narrow, It's narrow, it's very narrow, and also what? And long, and long. Then this will be regarded as adiabatic. That will be regarded as adiabatic. Or we assume that this separation between A and B is short and wide, then it will be diathermal. It will be diathermal. Those are the two answers that you can choose one from. Those are the two answers you can choose. So So the first question, which is going to be, just write question number one. Okay, I think yeah. So this question will be on the first answer. You can choose adiabatic. Adiabatic. Then you justify that if the separation, between A and B between A and B is long and narrow. Then we will regard it as adiabatic. Or we say diathermal. Diathermal. If the separation between A and B is short and wide. Someone can come up with another way of answering this question because it is a type of question that will need you to think about it. That's why I asked you to take your time, think about your answer. And this is my answer. So you can pick one of the two. You can pick one of the two. Then you get yourself full marks. That's one of the strange things about this module. Doesn't matter how big the question is. If you deserve 10 marks, you'll get it. Then we move to the next question, which is based on figure 2. Depicts one mole of an ideal gas that is taken around a cycle A, B, C, A from an initial pressure P1, volume V1, and temperature T1, represented by point A. Okay, but if process CA is isothermal, is CA, this one is isothermal, temperature T1, okay, but and now they calculate the temperature T2 at the end of the isobaric process in terms of temperature T1. That's our first question. How will we answer that question? Uh, this is question number 2, and it's A. We have this equation. This equation that we know of P equal to N R T for ideal gas. But in this case, we will talk of P1 V1 equal to nRT1, because this pressure, volume, temperature are state variables. So we're going to have the equation for the first state and another equation for another state. P2 V2 equal to nRT2. That's another for another state, and it's for an ideal gas. So you can just write here an ideal gas. For ideal gas. And then again, we know that P1 is equal to P2 is equal to P2. Why are we saying that? Because they talk of what we call isobaric. Isobaric process. Okay. So in this case, we're going to have we're going to actually solve these two equations and equate them, knowing that we have P1, which is equal to this. They say we have V2 equal to 1 over 2 V1. I mean, it's V1 over 2. That's what else we have. That's what we know as well. This will make sense as we continue with the model. Just bear with the way of answering questions. You'll understand as you are attending the classes, as you are also attending the formal lectures. So we'll have here it's not u1 over 2, right? It's u1 over 2. And then we're going to have two equations, which is this one and this one. It's p1 a1 equal to n r t1 over this will be your first equation. Then p2 is a2 equal to n r t2. This is your second equation. And then they say you divide 1 by 2. Divide equation 1 by equation 2, and then you're going to have p1 over p1 over 2 equal to n r t1, and then n r t2. And then we have on this other side in here, we're going to have 2. All these things are going to give us 2. We're going to have 2 equal to t1 over t2. And then your t2 will be equal to what? Your t2 will be equal to t1 over 2. Okay. Good. Now let's move to the next question. They tell us about this number B, where we calculate the pressure P2 at the end of the isochoric process in terms of pressure P1. They also talk of what we call isochoric. Isochoric. You have to know what it means. You know what isobaric means? I said isobaric, which means you will have P1 equal to P2. That's isobaric. The pressure is going to be constant. And then we say isochoric. Okay, allow me to move to the next number B. And so we are saying isochoric. It means V is constant. Meaning V1 is equal to V2. But for process process BC P1 V1 equal to NR T1 and P2 V2 equal to NR T2. Process BC in the diagram, you can see what process BC actually is. You can see process BC. And then from there, what are we going to do now? We know that T1 is equal to what? 1 over 2 T2. It's T2. T2 equal to 1 over T1 over 2. And then what are we going to do here? We'll substitute where there's T2, I'm going to substitute. Say P2 V2 equal to N R T1 over 2. And then we'll say 2 P2 V2 equal to N R T1. And then we'll have what? We'll have NR, we'll have 2 V2 over T1 equal to NR. Okay. And then we also check the other equation here. This one. This one, right? If you make an R subject to the formula, you're going to have, it's going to give you P1 V1 over T1 equal to NR. So you can substitute NR. So it's going to be 2 P2 P2 V2 yeah, 2 P2 V2 over T1 equal to P1 V1 over T1 is T1. So this one and this one can cancel each other. This one can just vanish when you have something like this. You just multiply by T1 both sides, and then you have 2P2 V2 also P1 V1. And also, what do we know about isochoric? V2 and V1 are the same. So you can choose to put is it V1, where there's V2, you can put V1. 2P2 V1 equal to P1 V1. Then 2P2 V1 equal to P1 V1. P1 V1. And then you can also cancel them with this place. So you have P2 equal to P1 over 2. Okay. Good. And then now let's continue to the next question. Is the work done on a system or by a system? Just for your answer. What can you say about this? Is the work done on a system? What happens if the work is done on a system? You have to know. You have to know what is it that you see when the work is done on a system. So we can see that this one is our, they say is our is our isothermal. T is remaining the same there. And also, but the important thing that we need here is that we can calculate the work done before and after. And to do that, first of all, okay, we know that, or the answer is that the work is done by the system. Let me see if the answer is clearly written. Located here. It's done by the system. The work is done by the system. I will give you a justification. And still looking for it here. I can't find it. But yeah, the moment I get the justification, I will write it. I will give it to you. So yeah, just write down that the work is done by the system. I mean, yeah, it's not done on the system. It's done by the system. The work is done by the system. So I don't want to write. I don't want to give you wrong answers. So this is number C. Right. It's number C. The work is done by the system. The work is done by the system. I'll give you the justification. And now let's move to number D. Number D, calculate the network done in the cyclic process. How do you calculate work done? How do you calculate work done for such processes? So you have to use the first law, second law of thermodynamics, blah, blah, blah. Yeah, actually this one, I would like to check it, and also this one out of the whole question paper. The rest, I will write them here. I'm gonna come back with number D and also the justification because I'm not sure about my answers as of yet. But as for these ones, let's continue. Number 3A. Number 3A. Number 3A. Question 3. Question 3. The first number A is going to be dV equal to dou V over dou T. P T plus dou V over dou P T dP. Then number B, you have dP equal to dou P over dou T V dt plus dou P over dou V T dV. 5 marks each. It's going to be 5 marks for each question. And then we move to number C. Number C. we have dv equal to dou v over dou t plus dou v over dou p t dp. Then eliminating 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 dp, we have dv equal to dou v dou t p dt plus dou v dou p t dou p dou t v dt plus dou p dou v t dv. Then this will be dv minus dou v dou p t dou p dou v t dv equal to dou v dou p t dou p dou t v dt plus dou v dou t p P dt. Okay. This will be one minus dou v dou p t dou p dou v t dv equal to dou v dou p t dou p dou t v plus dou v dou t p all applied by dt. And now say when dt equal to 0 and dv not equal to 0, 1 minus dou v dou p t dou p dou v t equal to 0. And we have dou v dou p t equal to 1 over dou p over dou v t. So this is equation 1. And then when dv equal to 0 and dt is not, dou v dou p t dou P dou T V plus dou V dou T P by 2 0. This is number 2. Combining 1 and 2, combining both the equations, then we get dou V dou P T dou P dou T V dou T dou V P equal to minus 1. And you also conclude that the partial derivatives are partial derivatives are noted in a way that the denominator of dou V dou T and dou PT is the numerator of dou P dou T V. And then you get yourself marks. Okay. Now we move to question number 4. We move to question number 4. Examine the following expression for the work done by real gases. Number A, what does what processes can it be applied to? That's the first question. What processes can this equation be applied to? The answer is for isothermal. Question number 4. Isothermal processes. Isothermal processes. For isothermal processes. And the next question, they say, show how this expression reduces to the one of an ideal gas. This is number B. I want to show how this equation is related to the real Gauss equation. Because this is an ideal Gauss equation. But this is at large specific volume. A over D and B become negligible, or we can neglect them. Negligibly small. Yeah, I can say negligibly small. They become small in a way that we can neglect them. And at low pressure, real gases behave like ideal gases. Therefore, if E and A over B are very small, we can neglect them. Neglect them. Therefore, W will be equal to NR T, the mean of VA. I think it's VB over VA. Yes, it's VB over VA. VB over VA. And you get your 4 marks, 15 marks. And then now we move to we move to the next question, which is question number 5. Question number 5. They say, with the aid of a diagram, show that the work done in an adiabatic free expansion is zero, even if there might be a change in volume. So how are we going to do that? It's question number 5. Question number 5. Then 5. First of all, what we do in the discussion is of to draw something like this. The diagram that you draw. Yeah, and then you have something like that. And here they say P equal to 0. And here you have something probably suggest and they indicate that P to be equal to 0. And they say in the diagram, a vessel is divided into two by a diaphragm. The space above the diaphragm is vacuated. What does it mean? It means the space above the diaphragm has no pressure. That's what it means when this is vacuated. And the space below is filled with gas. And the space below is filled with gas. But if a diaphragm is punctured, the gas will fill the entire vessel. The gas will fill the entire vessel. Very the end state would be the same if the diaphragm were a very light piston. Originally fastened and released. Fastened and released. Since the space above the diaphragm is evacuated, since the space then what? PE equal to zero. Therefore, the weight done will be given by this PE, which is what? Zero. Because this PE is equal to zero. So the work done will be zero as well. And yes, that's how we go about answering last year or 2023 test one question paper. Let's meet again in our next session. Okay.